Right. Good afternoon, everybody. Today I was supposed to start our discussion about pattern recognition or some methods in pattern recognition applied to data science. In particular, I was supposed to talk about graph theory applications in data science, but I ultimately decided that it's quite important that we talk about the second half of this file, the talk about the pseudo inverse in today in class because it's quite important. Probably it's one of the most important things that I discussed in insofar as linear algebra is concerned as applied to data science, because this will tell us how to deal with matrices that you will see in practice whenever you're doing some research or some theoretical work or some data collection or data analysis involving a large amount of information, right? So that's why I will insert it, and then I promise on Thursday we will move on and talk about graph theory applications in data science, right? So just a quick recap. In the past few days, we were talking about solutions to AX equals B, a linear system AX equals B. And if we know that A is invertible, then we have a unique solution. The unique solution is X equals A inverse B, right? So if you have a square matrix that's invertible, then you'll get the unique solution. However, we discovered some problems because initially this was not a problem when you were in college algebra, because almost all systems there are quite small, and most of the things that will be given to you have a an invertible uh, coefficient matrix A, right? But in theory or in practice, that's not always the case, right? So in general, right? So of course, even if A inverse exists, if A inverse exists, then you get the solution X equals A inverse B. But if A is a large matrix, there would be complications in the solution to this system. Even though we have an explicit form, finding the exact value of the inverse of A is quite a problem, right? Because matrix inversion is generally a very expensive process. Plus, if you are doing it in a computer, large matrices might have or it might result to inaccurate um, inverse for the matrix A. And usually we have big matrices in data science. So you need to be a little careful about using A inverse in your computations whenever A is a large matrix. Okay. Now, another issue that we encountered is when A is not square, or if it's square, what happens if it is not invertible? So that forced us to use a more generic solution to these problems. In particular, we look at the pseudo inverse. We said that the solution X could be written as A pseudo inverse B, where A plus is the Moore-Penrose pseudo inverse of the matrix A. And this is a generalization of inverses in the sense that all matrices have pseudo inverses, and the pseudo inverse of an invertible matrix is its inverse. So this is essentially our solution, and this coincides with the least square solution to the problem, meaning this is the vector that is closest to the solution, or if a solution doesn't exist, this will make the residual, which is maybe let's call it AX star. It will make the residual AX star minus B very, very close to the zero vector. So this is the ideal solution, right? So at this point, we have actually guaranteed, or at least we have nice ways to ensuring that we get accurate results. Accurate results in the computation because we avoided the computations of the inverse, which might have some issues insofar as machines are concerned, right? Then there were also some factorization methods that we looked at last time that addresses the problem of efficacy, or not efficacy, but rather the efficiency of the methods, because usually we do not have a very long amount of time to uh, to do the computations. We can't afford to run simulations that will last weeks or months, right? Because in data science, the turnover is almost or should almost be immediate, right? Once you have computations now. We are expecting some results in a few minutes because after a few minutes, we'll have a brand new set of data and then we need to incorporate it in the model, right? Now, the third aspect that I want to address today is the stability of the result, right? And stability, uh, especially for overdetermined systems, or sorry, for overdetermined systems, overdetermined systems. These are the systems wherein there are more rows than columns. There are more equations than the variables or the degrees of freedom. So if you go back to AX equals B, we will now consider the problem or problems when A is M by N. It has M rows and N columns, maybe complex entries, and M is much greater than N. Essentially, we have a lot more rows than columns. Because in matrix A, the rows correspond to data or data measurements, while the columns are associated with, so these are associated with the degrees of freedom, with the degrees of freedom, right? Now, hold on, let me add a page. Now, what do I mean here? Because usually, for instance, if you have a modeling problem, so you want to model, say, the population dynamics in a particular locality, right? And then you think there are several factors that should be incorporated into the modeling. So, for instance, you want to have, you know that the population dynamics is dependent on, say, the birth rate, then also the mortality rate, and say immigration, and say the carrying capacity, something like that. So yeah. So these are the degrees of freedoms, the degrees of freedom or the parameters into your model. And you want to find the value of this parameter so that you can match certain data. So for instance, you will collect data from, say, the first one you'll have here, data from location A, data from location B, data from location C, and so on, right? And then you will have, say, the number of people in location A, number of people in B, number of people in C, and so on, right? Essentially, we want a lot of measurements, right? We want to measure as many amount of information as possible to collect as many data as possible and then match it with unknown parameters. So there could be, say, 17 municipalities. So we'll be going from A, B, C until we get 17 of these guys. So there would be 17 data points. And then we only have 4 degrees of freedom. So we might have 17 rows and 4 columns for our coefficient matrix, right? Now, of course, this is a hyper simplified example. So in my research, I'm working with, say, 200 matrices with 200,000 rows and, say, 100 columns, right? So these are overdetermined systems, right? Now, one aspect of data science, again, the right-hand side may be coming from physical measurements. And we know that physical measurements are not perfect. There are some associated measurement error. There could be some noise in how data is collected and so on. So we need to factor that into our framework because those measurement errors might cause several problems, or that might cause a very high deviation from the actual values of the parameters than what we will be able to compute, even using the more Penrose pseudo inverse. Right? Now, from a more mathematical point of view, this is what I'm trying to illustrate earlier. So we started with the system AX equals B, right? So that's the perfect system, or this is the ideal system that we want to solve, where again, A is M by N, where M is much greater than N. Now, one question is, or going back to my problem earlier, is the problem would be when the right-hand side is tainted by measurement error. So what is this? Incorporates some measurement error or simply noise, right? So for instance, we want to solve AX equals B, but the right-hand side that we get from physical measurements will not give us exactly B because we have physical limitations for measurements, etc. So instead, what we might get is this. So instead of this, we will get a system that looks like AX equals B plus epsilon, where the norm of epsilon, say in the L2 sense, is much less than 1. Right. So that means we are looking at the actual data, the ideal data, but when you do the measurements, you won't get exactly B. You will get B plus epsilon, where epsilon is the error vector or the noise vector. Error or noise vector. So whenever doing physical measurements, this is the system that you are feeding to your computers. But what really happens in nature is the system AX equals B. The ideal scenario is whenever epsilon is small, the solution we get from this noisy system should be very close, should be proportionally close to the solution here. So for instance, let me solve this and say I get x1. X1 is A inverse B or A pseudo inverse B. And then X2 will be A pseudo inverse times B plus epsilon, right? Now, if epsilon is small, so if the norm of epsilon is small, then X1 should be approximately equal to X2, or there should be a proportional change in the solution that you get after you incorporated the noise, right? But that doesn't happen all of the times. So what we'll be looking at in the next 40 minutes or so is to look at tricks on how we can avoid the effects of the error vector. Again, we want the ideal case that whenever the error vector is small, there will be proportionally small change in the computed solution, right? So, and I'll share with you the one of the easiest way to do the regularization. So by the way, whenever you have this system, what we want to do is to regularize the solution. The regularized solution mitigates the effect of noise or measurement error to the actual solution. And again, what the target is actually make x1 close to x2 or vice versa. Probably it's much better to say that we want x2 to be close to x1 whenever the noise is quite small. Right? Now, um, I'll discuss one particular case, but there are more complicated and fancier and more theoretically involved regularization techniques. But what we'll discuss today would be the L curve technique. Right? So it's in the handout that you can see in Unit 2B. So you can download it there. But we already discussed Part A, so you should have a copy of this. So skip to page 18, I think, and then you'll get Section B, the L curve. Then I just mentioned here what I said to you earlier, and this is what we want. We want the solution from, okay, let me recall. The actual solution is called X star, and here the solution from the noisy system is X tilde. So we want the solution from the noisy system, from the system that is tainted by measurement error, to be as close as possible to the ideal solution whenever the measurement error is relatively small, right? Usually we want the size of the relative error to be approximately equal to or is proportional to the size of the error. So again, stability. We want stable solutions. Small changes in the right-hand side. If we have a small residual vector epsilon, then we must get a small relative change in the solutions. I mean, the ideal solution and the solution from the noisy system, right? Now, let's consider some things. Now, do we always need to worry about this particular scenario? Well, this ill conditioning or the ill posedness of a matrix is imminent whenever the condition number of a number is very big. The condition number of our matrix is quite big. So whenever you're doing some computations involving overdetermined systems, especially for larger ones, it pays to check what's the condition number of your coefficient matrix. The condition number of the coefficient matrix is usually denoted as kappa of A. Now, a common formula, there are several formulas for the condition number, but this is what we'll use, and this is also built in MATLAB. The condition number kappa of the matrix A is actually the norm of the matrix A, and it's times the norm of its pseudo inverse. So in MATLAB, you can write COND of your matrix A. So if you have a matrix A already defined in MATLAB, just type in cond of A, it will give you the condition number. The bigger the condition number is, the more sensitive the solution is to the perturbations to the right-hand side. So whenever you have a big condition number, you need to be very wary because the measurement errors will be amplified by some factor of the condition number. So do not trust the results whenever the condition number of your matrix is quite high. Because in particular, the relative change. So this is the relative change in the solution, or basically you can think of it as the relative difference, the percent difference between the solution from the perfect system and the solution from the noisy system, right? So that relative change, that relative difference is bounded above by the condition number times this is the relative size of the noise. It will tell you what percent of the actual right-hand side is the error, or is the noise, right? So this will tell you what part or how big is epsilon compared to the right-hand side vector. Essentially, this is telling us that the relative difference between the noisy solution and the ideal solution is bounded above by the condition number times the relative size of the error. Okay. Now, to make this clearer, let's consider one quick example. Example 9.4. Suppose we have this system AX equals B, and then we have here a 3 by 2 matrix. So it's underdetermined. This is overdetermined, although it's still a small matrix. And we have the right-hand side 0.25, 0.26, and 3.32. Okay. Now, I'll show it to you later in MATLAB, but if you do the computations, you'll get kappa is 629.5801. So whatever the size of the noise that you introduce or that you incurred during the measurement of the right-hand side, it will be amplified by 600, around 630 times in terms of the relative difference. Okay. So for instance, okay, just take note that the solution, the exact solution is the vector 1, 1. Okay. Now, if you will introduce this perturbation, the relative, this is the noise to the measurement. So that's 0.001 minus 0.02, then 0.01, right? So that means instead of this right-hand side, what you gathered from your measurements or from your whatever data collection technique you use, this is not what you got. You were tainted by this noise. So your B plus epsilon is what you got from your measurements, and that's going to be what? 0.26. Then you have, I thought I could do the math uh, mentally, but this is 0.26 minus 0.00 minus 0.032, and then you'll have, instead of 3.32, you'll have 3.33. So this is the right-hand side that came from erroneous measurements, or this is the noisy data, and this is the perfect data. Now, this noise is actually just 1% of, or about 1.05% of the right-hand side. Essentially, you can think of it as about 1% noise or 1% measurement error. So if you're thinking about a stable system, that 1% change in the right-hand side should just cause a relative difference between the actual solution and the noisy solution of about, say, also 1%, or the same order as 1%. So between 0% to say 10%. You can roughly say that that's a stable system. But since we know that kappa, the condition number is 629.58, so about 630, that means the size of the noise will be amplified 630 times in terms of the relative error for our or the relative difference between the noisy solution and the actual solution. That means in the worst case, I am expecting that that 1% noise will result to 660% difference in the solution that I get. Okay. Again, if you will just solve the system, the exact system as it is, using perfect data right-hand side, what you're going to get is 1, 1. That's your solution. But if you will solve it a using a right-hand side data that is tainted by 1% noise. So this is the 1% noise that we have, and then I'll uh, I'll add that to it. If I'll solve the system, the solution that I'll get is this guy, minus 2.99, comma 7.22, which is quite far from the actual solution 1, 1. So that means if there is no noise, the actual solution is 1, 1. If there is a 1% noise, the solution that we'll get is close to minus 3 comma 7.22. And that is quite far from each other, right? Do we get an accurate result? Yes, we still get an accurate result, because if you compute the residual, so you get AX tilde, A times the computed solution minus the noisy right-hand side over the size of the noisy right-hand side. So that means our pseudo inverse computation is good. The error is about 0.56%. So we get good results with respect to the noisy data. So we are modeling the noisy data nicely. But remember, this is not reality. We want to model just B, right? So if you take away the measurement error or the noise, you will get, we should have gotten 1, 1. That's the exact solution. But what we got is this guy, which is quite far from the actual solution, right? In fact, how far is the noisy solution from the exact solution? Then you take the difference of the two solutions, and then take the size of that vector, then divide it by the size of the actual solution, or the norm of the actual solution, and you'll get 500 or 5.227. That means there's a 522% difference, or close to 523% difference between the noisy solution and the exact solution, right? And that is true because it's bounded by 660, which is kappa, the condition number, which is 629 point something times 1.05%. All right. So imagine you are in the medical field, and you're computing where to stick needles in your patient's say in your patient's body. You should target 1, 1 if you will be using perfect data. Your computations will tell you you'll need to stick needles in coordinate 1, 1. But if you're tainted with 1% measurement noise, and since we have a very ill-conditioned matrix, then this is where you will stick the needle. And that's quite far from the target 1, 1. You are off by 522%, even though you're modeling the noisy data well, but you're not modeling reality, because your purported solution for the realistic problem is 522% off from the actual solution. Okay, so we need really to be careful about ill-conditioned matrices. And I'm not even working with very huge matrices. This matrix has size 3 by 2, and yet I see the stability of this system. All right. So what we will tackle really is how to avoid that particular scenario, right? Now, whenever we're looking for the pseudo inverse, the least square solution, this is our target. We want to minimize the L2 norm of the residual. We're looking for the matrix X star that will minimize the L2 norm of the residual, or the square root of the squares of the errors. So essentially, that's your statistical least square solution, right? But Tikhonov proposed that we need to do a regularization to take away the to take the stability, to take the instability away from the problem, right? So instead of minimizing just the residual, or essentially you are here concerned with the accuracy of your solution because you want the error to be very small, we look at minimizing this guy. So our solution will be the vector x alpha, which minimizes the sum of two things. First, we are minimizing the error. So this term, minimizing this, accounts for the accuracy of our solution. Then this added term actually takes care of the stability of the system. Right. So essentially, this is a two-pronged attack. We want to minimize the error and at the same time minimize the instability of the of the system. Okay. Now there is a question here. Okay, this is fine. This is the L2 norm of our residual. This guy is the L2 norm squared of the size of the solution. But we have here a multiplier alpha that sort of balances the contribution or the weight that we give to accuracy against stability. And this alpha is a regularization parameter chosen between 0 and 1. Usually it's a very small a very small positive number. Now, how do we get alpha? That's where regularization or Tikhonov regularization methods vary. There are several ways on how to find alpha, but here what I want to do is to solve for alpha using the L-curve technique, right? I guess this is the easiest one to implement, and I'll share with you a code that will exactly do that, right? Now, so this is what you want mathematically. I'll give you the algorithm, how to get the solution x sub alpha. But first, we need to decide what is that parameter alpha, okay? So first, now, this is quite a brute force approach. That's why it's easy. There's little math that is to be done, but this will be in brute force. So we need to do a lot of computations and choose among the solutions out of those many computations. And then the best one will be declared to be our optimization parameter alpha, right? So essentially what you'll do, you'll get some candidate alphas. So essentially you start from the interval 0, 1, and then we choose, say, 10,000 points or 10,000 possible alpha values between 0 and 1. If you can afford using more alphas, say you use a million alphas, then you can do so. And then for those million alphas, what you will do is you will compute for this guy. So this looks familiar because essentially this is our pseudo inverse. Oh, sorry, this guy is our pseudo inverse. That's a pseudo inverse solution. That's the least square solution. But the Tikhonov regularized solution incorporates a perturbation of the diagonal. Okay. So just to recap, so we know that alpha belongs to the interval 0, 1. Then we need to pick some representatives from 0 to 1 and get a number and get the solutions from each of these alphas. Right. So say you have 10,000 numbers between 0 and 1, plug it in, plug each of them into this guy, right? And then compute what's this vector, right? So for each alpha, you're going to get one vector. Now, for each of those vectors, you need to compute the residual, right? So each alpha will give you a residual computed as the L2 norm of the error. Meanwhile, each of these alphas will also give us the norm of the solution. So each alpha, just compute the L2 norm of that X alpha that you get. Okay. So you have the residual norm and you have the solution norm, and then plot them in a two-dimensional plane. All right. So you will get the graph that looks like this. Okay. So you have the residual norm on the x-axis. So you have, say, if you chose 1,000 alphas, you're gonna get 1,000 residuals or residual norms, and then you'll get 1,000 solution norms. Plot them in a coordinate plane with the x-axis comprising of the residual norms and the y-axis consisting of the solution norms. Right? Then you will get a plot that will usually look like an L, and hence the name, the L curve. Okay. And then you will pick the alpha that gave you the chord. So this is our optimal choice, or the alpha that gave us this point will give us the optimal choice, right? But it's a little bit hard to find that alpha because we don't see alpha in this picture, right? So you have the residual norm, but each of these residual norms were obtained by using different alphas, right? Then the solution norms are also computed using different alphas. Alphas are actually hidden in this plot, but essentially we need to have a nice way of retrieving what was the alpha that gives us this particular point. I'll share with you the code that I wrote, the simple code that I wrote to give you a graphical way of computing for that alpha. Well, there are several techniques on how to get that alpha. But that would be, but those methods are quite mathematically involved. That will require some nonlinear optimization. And we are not discussing that here, so I'll stick to a graphical solution. So essentially, in summary, you have various candidates for alpha, compute X alpha for each of them, and then plot the residual norm versus the solution norm. Once you get the plot, you'll get the quarter. And the alpha that gave you the quarter should be your choice for alpha. Okay. Now probably let's look at the example here that I have. Okay. In this particular example, I have, we will resolve example 9.10 or system 9.10. Let me just recall what system 9.10 is. Oh, that's the one here. Yeah, this is our system. And this is our perturbation, right? We have learned earlier that the 1.05% relative error will cause or will give us a solution that is around 522% away from the actual solution that we got. Okay. Now I want to reduce that number. I want this to be significantly reduced. Right. Now, let's see how it is done, right? At least the outline, then I'll show you how it is how we can implement this in MATLAB using the code that I will provide. Okay. So first, you need to construct the L curve, right? So in this scenario, we have an alpha interval, say machine from 10 to the negative 16 to 1, because usually computers have precision 10 to the minus 16. So virtually this is 0 insofar as most computers are concerned. So we are choosing 1,000,001 alphas from this interval, from 10 to the minus 16 to 1. You choose 1,000,001 candidates for the best alpha, right? Now, for each of these alpha values, okay, so I will have 1,000,001 alpha values, then I will calculate X sub alpha using formula 9.12. This is formula 9.12. So I will have 1,000,001 X sub alphas. Okay. And then for each of these X sub alphas, I will I will construct these points. I will compute the residual. I will compute for the solution. Okay. And then I will plot them in a, say, logarithmic plot, right? Then I'll get this L curve. Again, the corner of the L curve is our optimal choice for alpha. So I need to retrieve what was the alpha that was needed, right? Or that was that alpha that gave us this corner. All right. I'll show you later how. But if you do that, you will if you will get what I forgot. I think I wrote the alpha, right? The alpha, the optimal alpha that I got from the routine is about 7.81 times 10 to the negative 4. It is saying that 7.81 times 10 to the negative 4 is the balancing weight, or it's the near optimal balancing weight between between maintaining the accuracy of the system and maintaining the stability of the system, right? And then we will now retrieve X alpha. So we'll have X sub alpha equals alpha I plus A, let me check 9.12, A conjugate transpose times A inverse, then A conjugate transpose times B, right? And our alpha here would be 7.81. That would be my best stable solution, right? And if you compute that, this is what we'll get. Remember what our target was? Our target was to get 1, 1. That's the solution from perfect data. Now with the Tikhonov solution, this is what we obtain. 1.08 comma 0.87, which is much closer than what we have gotten using only the uh, the least square solution, right? Now you do some quantitative test if this is good or this is bad, right? So this is a good solution because it models the noisy data well. The data it models the noisy data with error of just about 1.03%, right? This is a little bit higher than what we have gotten from the previous example or without the Tikhonov routine, right? Plain old pseudo inverse technique gave us an error of 0.56% from the previous example, right? Without regularization, the error is 0.56%. With regularization, we gave up some of the accuracy. So we allow the error to be to almost double or to more than double to 1.03%, but we should be gaining something. We are giving some of the accuracy up in favor of stability, right? And I think it is quite evident because this is the solution that we got, and this is actually what a perfect data would have given us. And if you look at what is the relative difference between the noisy solution and the solution from the ideal data, this is what we'll get. So that means we have around 11.13% deviation, right? So that means the 1% noise, the 1.05% noise just changed the solution that we obtained by 11%. And this is quite a big leap from the previous result that we got. Remember, without regularization, uh, the 1.01% noise caused our solution to deviate by about 522%. Now that 522% is down to only 11%. Right? So that means going back to our patient problem, we want to inject them at location at coordinates 1, 1 in their body. We got very off results with the previous one, but using the regularized solution, you're quite near now. You are 1.08 comma 0.86. So that's still within 11%. So you are doing a much better job in this particular scenario. Okay. So I think that's the entirety of the use of the L curve technique. Now let me show you how it is implemented in MATLAB. Right. I'll share with you also the file, but let me change screens. Okay, hold on. I already forgot how to change screens here. Oops. Okay. I'll stop presenting from my tablet, then I'll go to my main screen. Then I'll share with you MATLAB code. Hold on for a second. Okay. So I hope you're seeing my MATLAB screen now. So here I have the MATLAB file or the MATLAB script lcurve underscore sample.m. Okay. Now here I have, hold on, let me have my mouse. I will initiate the problem parameters or the problem, they call this, the problem parameters, right? So I have here the matrix A. This is the one this is the one given in the slides. And then we have here 0.025, 0.26, and 3.32. Let me just double check. I guess this is the right-hand side we have. We were given, that's the perfect data, right? and then we are trying to perturb this, put E here. We are assuming, say, that the error is, or the noise is 0.01, so 0.01, semicolon. I'll use semicolon because I'm working with a column vector here. So semicolon says next line. So then minus 0.032, minus 0.022, and then we'll have 0.01, 0.01. Okay, that's going to be our E. And then, yeah, let me just run this. So you can run parts of your MATLAB code if you want to debug it or to run it piece by piece so that you can track errors down easily. So you can right click here and then choose evaluate selection in command window. So you'll have the matrix A, B, and E here. Then if you want to know what's the condition number of the matrix A to know how big is your the condition number. So just type cond, C-O-N-D. Look at here. I am typing at the command window. So I have cond of, hold on guys. I think all right. Anyway, I lost my the connection to my other device. But if you look at the command window, the highlighted one, it says cond. That's the built-in command for the condition number. You simply type inside parentheses the matrix that you want to compute the condition number of. And here, this is the number that we got from the module 629.5801. So that's the condition. Then if you want to know how big is this, or yeah, so that's the condition number. So we're expecting 630 times amplification of the error. If you want to know the size of the error or the noise that you have, so we compute the norm of B, the norm of E divided by the norm of B, right? So this is to know what percent is the error or what is the relative size of the noise with respect to the right-hand side vector. We compute it, so you get 0.0105 or 1.05% that you see in the slides. Okay. Now, okay, then I go to line 13. This creates a vector of alpha values. So this generates the list of candidates that we have for our solution. So it will create a vector starting from 10 to the minus 16 with increment 10 to the negative 3 until it reaches 1. In the in the modules, I use 10 to the minus 6 increment. So the number in the middle tells you how much is the jump between one possible alpha value to another. Just to save time, because it might take quite long, I'll replace minus 6 by 3, right? Then if you run line 13, okay, you will have an alpha. If you look at the workspace here on the right portion, alpha here, the vector alpha consists of 1001 candidate alpha. So I have 1001 candidates for the optimal alpha value, right? That's fine. Then for each of these 1001 alpha values, I will compute the solution norm and the residual norm. So I just need to run this uh, this for loop here, 16 to 21. Then it might take quite a while, especially if your alpha or if your alpha vector is quite big. Here, I only have 1001 candidates, but if you want to replicate the ones on the slide or the solutions in the module, you'll need 1,000,001 alpha values. So you need to replace the middle number here. Instead of 10 to the minus 3, you make it 10 to the minus 6. So that will give you a finer mesh for alpha. You will have more candidates for alpha. Okay. Now just run line 16 to 21. Okay. I added line 20 to let me know that the iterations are being carried out, because you will have the iteration number done so that I know how far along I am in generating the alphas. Okay. So just run that part. And then lines 23 to 27 will run or will give us the L curve, right? So I'll run that. I'll give this, I'll get this L curve, right? All right, so I get this L curve, but hold on. This L curve is quite different from what I have. Uh, uh, oh yeah, it's, hold on. Ah, that's the problem. Ah, yeah, that's not exactly the L curve that we saw in the that we saw in the modules. The reason is I forgot to uncomment line 10. I need to run line 10 because I will change the right-hand side that I will feed into my program by the perfect data B plus the noise. So that will update the right-hand side vector B to incorporate the noise in the modeling. So I'll run that so that B is updated now. Then I'll redo the computations from line 13 until lines 27 to get the L curve. So this is the L curve, which is quite similar to what you got in the slide, right? And then how do we get that alpha values? So that's the job done by lines 29 to 33. I'll just illustrate what this will do later or what these lines will do, right? So this will just allow us to click on the corner and that will give us the alpha that gave us that particular corner because really the problem is harvesting that alpha, right? So I don't want to go into the extra details, but trust me, just run lines 29 to 33. Okay. And then there are some additional lines here, but essentially this the code will end up with the X alpha. This is our optimal solution with respect to the L curve, right? Now the final solution will be stored in the vector X alpha, and the optimal alpha among the thousands of candidates that we put forth will be called alpha optimal, right? Now, if you're good with the actual code, so we just need to press run here in this corner. Okay. Sorry, not in the corner, but in your tab, right? So it's up here. Either you click run or you press F5 on your keyboards. So I'll press run. Computations will be done, and then now I have a crosshair. Right? If you see here, I have this kind of cross or the target, right? So you can move your mouse and then move it until the crosshair locks in into the corner of the L curve. And then you need to click it once. Once you click it, there is a checker that will give us a smaller picture that indicates what's the point that we clicked on. Right? So we click on here. So it seems that we indeed click the corner. So that will be stored into MATLAB. That will be passed on into the workspace. And if you go back to MATLAB, just minimize all the figures that you generated. And you look at the workspace, you have your optimal alpha. Since I only have 1001 candidates for alpha, I got 0.0020 as my optimal alpha. So I can also type alpha opt in the command window, but be careful with the cases. So MATLAB is case sensitive. Press enter. So we see that we get 0.0020. That's the optimal alpha. Then what's the solution that we got? Just type X alpha in the command window, and we'll get this vector, 1.1342.7968. Okay. Now, to check, did we model the noisy data well? So in order to see that, we need to compute for the relative error. Relative error, again, is the norm of the matrix A times the noisy vector, A times X alpha minus the noisy vector B. So this will tell us how big is the error. But since we want to know the percent error, I will divide it by the norm of the right-hand side B. And here you get 0.0104. So meaning we are modeling the noisy data with precision or with error of just over 1%. But that's not really what we're concerned with insofar as stability is concerned. So we just described the accuracy of our method insofar as modeling the noisy data. But what we are more interested in this kind of problem would be the relative difference between the ideal solution and the solution we got from the noisy data. So what we need to compute for is the norm of x alpha, that's our noisy solution, minus the actual solution. Remember, the actual solution is 1, 1. So I'll just type that in here, and then I'll divide it by the norm of 1, 1. Sorry, norm of parentheses, and then the vector 1, 1, and bracket and parentheses, then I'll get 0.1722. So meaning I have the 1% or the 1.05% noise caused 17% change in the solution that we obtained. But that is quite fine because it would have been 522% if we did not do the regularization. Okay. So I think I will end the discussion here, but I want you guys to try on your own. Okay, in the remainder of the time we have for today. Example, let me see. Scroll down to the handout. So exercise 9.6. Okay. Now try this one out. I will also upload ex96.mat. That's a MATLAB file that contains the data for this exercise. The size of it contains. So let me just clear my workspace. Then I'll load ex96.mat. If you have downloaded the file ex96.mat, you can just double click on it on the left panel, like that, and then that will be loaded into your workspace. So you have the matrix A is 32 by 32. Then you have the matrix B that's 32 by 1, or the right-hand side vector 32 by 1. But this right-hand side vector is actually the perfect data, right? Now, I think I need to illustrate this part to you, but let's see. Now, since the B that we loaded, the right-hand side vector we loaded is the perfect data, I need to simulate some noise to it. So you can just uncomment lines 8 and 9. Sorry. Since we already have matrix A and B in the workspace, I need to comment this guys down. So can just 5 to 7. So highlight. So let me just do that again for those who are not familiar with MATLAB. So I'll highlight lines 5 to 7 because I don't want to compute A, B, and E this way now because I already have the matrix A and I have the vector B, and then I will construct the noise vector E later. So I don't want this to be done by MATLAB. To instruct MATLAB to ignore lines 5 to 7, you need to highlight it and then go to the top ribbon. Okay, in the top ribbon you will see the percent sign, and this is the comment command, right? I hope you see my cursor. The comment R, or you can press Control R after you have highlighted the lines that you want to be commented out. Commented out, a percent sign before a line tells MATLAB to ignore whatever follows the percent sign, right? But now I will uncomment lines 8 and 9. So there is a percent with a cross in the top ribbon. Just click that so that the comments will be gone, right? So you can highlight and then press the decomment or the uncomment button on the top ribbon, or you can just simply delete the percent symbol on lines number 8 and 9. So line 8 will give us a random vector of the same size as the right-hand side vector B. And then it will be normalized so that it will be 1% of the actual right-hand side vector, right? Because MATLAB, I think, will randomize, or when you run line 8, it will give us a vector consisting of numbers from 0 to 1 that is normally distributed. But I want the noise to be around 1% of the right-hand side. So I need to scale it down. And for that, we'll use line number 9. And then line number 10 will update the right-hand side vector that will be fed into our computing software as B plus epsilon, or B plus. maybe I should add here uh, a variable orig b for to stand for original b, so that I can store the original b value that came from that represents perfect data, right? Then we can run this, run everything now, and then this is the L curve that you will get, something like this, right? And then you can click on the corner, the crosshairs. You look at the crosshairs, put the target to the corner, and then click once. And then, yeah, I missed the target a little bit. So this is what I click. I was aiming for the corner, but that's fine. Let's see what we get. So yeah, the X alpha that we get is the optimal alpha. Alpha optimal is 0.003. The X alpha that I got is this long vector over here. Okay. Then I want to compute, I want to see the accuracy. Did we model the noise data well? Well, you compute the relative error. So get X alpha minus, this should be, what? Sorry, this is not the norm I'm looking for. Yeah, this is A times X alpha minus B over norm B. So we have 0.57% error. So we are modeling the noisy data well. But how far did we deviate from the actual solution? Well, I don't have the actual solution here, but you can compute it by taking X alpha minus, this should be pseudo inverse of A times orig B, or the original B. And then you divide it by the norm of the original B. And you see that we have 3.67% relative difference. So that means the 1% noise that we introduced that could have been due to measurement error or to noise in the data per se caused a relative difference of 3.67% from the noises, or from the solution from noisy data versus the solution from perfect data. Okay, which is very good. Well, is it good? I forgot to answer whether the matrix A is ill conditioned. So just type cond of A, and you get 2.7025 times 10 to the 70, right? So that means if this guy, the upper bound for the relative difference would have been the condition number times 1%. So we should have expected a relative difference of about 2.70 times 10 to the 15. In percentages, that's 10 to the 13%, which is very huge. Okay. Now, and look at the improvement that we got. Instead of this guy as the relative difference, 2.70 times 10 to the 15, the relative difference now is simply 3.67%. All right. So try to play this out. Some things that you can play out. Well, I randomized the vector here. So every run of this code will give you a different L curve and a different error vector. So you can play with it. Another thing that you can play with is to consider a denser mesh. If you have the time to wait for a longer simulation, change the number in line 14. Instead of 10 to the minus 3, the middle number, you can change it to 10 to the minus 6, or change it to 10 to the minus 8. Then you'll get more alpha values. Okay, then compare your answers. So try it out. Follow the instructions in exercise 9.6, and let me know on Thursday if you have some questions or problems with this. All right. So with that, guys, I hope you got something from this video. Just let me know on Thursday if you have questions. I hope by then you have tried answering exercise 9.6. All right. Until then, guys, keep safe and thanks for watching the video. All right. Bye bye.